In the last video, we saw some area applications, or I guess graphical applications of the fundamental theorem of calculus part 2. Here we're going to look at the algebraic applications of the fundamental theorem of calculus part 2. So let's say that we are given some g of x function, and it's defined in a weird way, right? It's defined as an area accumulation function. Our function g of x is going to be equal to the integral from 0 to x of sine of t dt. Notice these variables are not the same because they aren't representing the same thing. I could draw a picture of this, that this is going to be as I start accumulating areas under this sine curve, I'm going to get out this new curve, g of x. But this question isn't asking us about the graph. This question is asking us, what is the derivative of this function? At the face value, it looks almost overwhelming. Thankfully, that's actually exactly what the fundamental theorem of calculus part 2 tells us. The fundamental theorem of calculus part that for a function, I guess, that is defined in this way, we have that, maybe I should restate what it is. For some area accumulation function, g of x, that's equal to the integral from a to x of f of t dt, we have that the derivative of our area accumulation function is the inside function evaluated at f. So to apply the fundamental theorem of calculus part 2, we find that g prime of x is exactly sine of x, and we're done. Because the derivative of an area accumulation function is the inner function evaluated at that variable. That was too easy, you say, and I say, hooray for too easy, right? It's just an application of the theorem. So let's look at something that's a little more difficult. Suppose we have g prime of x, or suppose we want to find the derivative of this, but our function is changed slightly, right? In this case, our function g of x is equal to x squared sine of t dt. So instead of being an area accumulation function rolls out sort of at a steady pace, it means that our accumulation of area is actually going to be dependent upon this function up here of x, this x squared. So it's going to start accumulating slowly, and it gets faster and faster and faster with an x squared type fashion. And it turns out we can still use fundamental theorem of calculus, but we need to apply chain rule. Because in this case, we actually have a composition of functions that I can think of. Maybe I'll say g of x is equal to some function of x. And so in this case, if I want to know what the derivative of the outside function is, well, it's a composition of the derivative of the outside and this inner. So by the chain rule, we can see that g prime of x is going to be equal to the derivative of this outside function, which we know previously by fundamental theorem of calculus is just sine of x, but I have to be sure to multiply by the derivative of the inner function, f prime of x. And in this situation, because our f function was equal to x squared, we can g prime of x is going to be the sine of x times the derivative of that upper function, which the derivative of x squared is 2x.